So, we've learnt about how to differentiate, but how can we draw the derivative for a function? Well, today I'm going to give you a few handy hints and tips as to how you can etch out this function. I've got up on the board a function, f of x here, and what we're going to do is we're going to look at the slope and survey what is happening to the slope in order for us to draw the derivative of this function. So, a few key words and a few key phrases are increasing and decreasing slope. The slope here is increasing. The slope here is decreasing. What we need to know as well is that the f primed of x is going to be equal to 0, or a stationary point. Something I just want to do on my set of axes is actually draw the Cartesian plane. Okay, so now we can start actually considering this function f of x. When the first derivative is equal to 0, we have what is known as a stationary point. This here is a stationary point on the original function f of x. Another stationary point and another can also be seen over the function. There are three stationary points: a local maxima, another local maxima, and a minima. So, let's have a look at the trend line. It's starting to increase at an increasing rate. It's becoming quite steep. So because of this, we need to consider whether the slope value would be negative or positive. Because it's increasing, the value is of course going to be positive. So if we were to etch out this curve, it would appear as though the function gets really steep in terms of the increase up until a certain point at which it decreases. You can see this from the actual diagram here, how it gets steeper and then eventually fades off again. So, let's start drawing this and interpreting this. You probably have it starting at some position, maybe here in the positive derivative side. It would become more positive up until a point, and then it would start easing off in terms of the positive nature. And remember that at this stationary point, the derivative is going to be equal to 0. The reason the derivative is going to be equal to 0 is because if we were to draw a tangent line there, it would have no slope. So, if the function f of x has no slope, the derivative is 0, because the derivative is just the slope of the function. So that means we line it up with the 0 coordinate. Now the function has a negative slope that is becoming more negative up until a certain point. So we can draw this on our function. The f prime of x will go in the negative side of the Cartesian plane, the negative quadrant, for y. And then, when we reach what's known as a proximate point of inflection, where the function actually changes from concaving, where it forms a cave shape, to convexing, where it forms a bowl shape, that's when we start moving back up again. And then, by the time we get to the stationary point, we will be back at the actual intercept on the x-axis. Because of course, the slope of the tangent for the f of x is of course where the f prime of x is going to be equal to 0. Now we need to consider what also is happening to the slope. It's going up again, and the rate of increase is increasing. We can see it here. And then, after a little while, it starts to fade off. Remember again that we also have a third stationary point. this is where our function f prime of x needs to cut the x-axis. And after a certain point, the rate of increase actually decreases a little bit, and we sort of get a curve like so. And now lastly, we can see that we've got a negative slope that is becoming more negative. Hence we can continue the curve. And now we have it. The f prime of x, the first derivative of our f of x function. Let's just check through this and make sure we've got it correct. I like to label my parts of the function. So we have an increasing function, and the rate of increase is increasing up until around about point A or so. Then after point A, the function is still increasing, but the rate has decreased a little bit. So we have an increasing function, with a decreasing rate of increase. Are these two things reflected in our derivative? Well, let's have a look. Increasing means that we have a positive slope. Yes, we have a positive slope, and it's increasing up until a certain point, and then the positive slope actually decreases a little bit. But it still remains positive, the derivative, up until the stationary point, which I've labelled on the diagram now as B. So let's check the next part. We probably have an inflection point C here. What's happening to the original function f of x is we have a decreasing function. Hence the derivative will of course be negative because it's got a negative slope, it's going downwards. And the rate of decrease is increasing. As you can see, it's sort of becoming more and more steep up until a certain point. That is known as a point of inflection. Point C. And we've reflected this here. It's becoming more and more negative up until an inflection point. And then we have a decreasing function for the original function. And the rate of decrease, the rate of decrease is decreasing. And that means that we're starting to get something that's actually getting back to a slope of 0 because the rate of decrease is decreasing. Hence, that is reflected in our derivative. Because it's heading back towards the positive quadrant, it's becoming less negative. And then, for the rest, we have a similar sort of thing. It's just like the original curve we had, but slightly different. And again, that's reflected within our first derivative. So that's how we can analyse slopes. A few key pointers that might be able to help you out. Consider whether the function is increasing or decreasing. Consider whether the rate of increase or rate of decrease is increasing or decreasing. And always remember, if there's a stationary function, stationary point on the function f prime of x, then we know that it's of course going to be 0 when we draw our derivative, because the slope of the tangent is going to be 0. If you want to, you could go ahead and do a bit of extension and look at actually drawing the second derivative for our original function f of x. I'll give you a few pointers for that as well, but we'll also be looking at the second derivative in my very next video, and a few videos after that as well. But if you wanted to attempt it, the f prime prime of x, so the second derivative, again, you just need to essentially have the idea of differentiating twice, but when that's equal to 0, we have those inflection points. And the inflection points are like C and A on the diagram. They represent where the actual function, f of x, is changing from concaving to convexing. And in terms of the f primed of x, again we can use the logic that the stationary points on the f prime of x, this time our derivative, will actually be where the second derivative, f prime prime of x, has an x-intercept value. So, feel free to continue on doing that if you're interested. Hopefully you've been able to follow along with drawing derivatives. It can become very handy, and it can also help you predict and analyze what is happening to a slope. Remember, functions are all around us. There are many real-world applications, and in a future video we're going to be looking at how we can use calculus to actually look at the physics all around us. So, until next time, that's all for now.